All right, welcome back to our third session of the Chemistry Review here, sponsored by Learn America. And today what we're going to do is continue on our sequential order of, we started with the atom, and we built from the atom into the elements. And today what we're going to do is talk about compounds. All right, we're going to now take the next step, combining the elements to develop compounds. And we're going to discuss the concept of how does that happen. So let's start our session with just a quick review of the difference between atoms and ions. Okay? An atom is the fundamental particle that's inside the element. And in the last session we discovered that there are different kinds of atoms. There's metals and nonmetals and metalloid atoms. And the metals have the tendency of losing their valence electrons and therefore becoming what we call cations. And the nonmetals have the tendency to draw electrons to themselves and become those anions. So the fact is, what's transferring, what's being shared when these compounds are created is those valence electrons. So that's a key component of how chemistry works. Again, the anion is the negative ion that somehow has gained electrons from a metal, for example. A non-metal would draw the electrons away from a metal, so a fluorine atom would become a fluoride ion. It gained one electron and now has a -1 charge. Oxygen atoms would gain 2 electrons and now has become the famous oxide ion. Now these are the things that we typically come in contact with in science and in real life. Like we brush our teeth with fluoride, right? We have oxides everywhere. For outside in the rocks, there's many different types of oxides. The difference is what metal is connected to these anions would determine the different kind of compounds we're working with. And those metal atoms, they become cations. Cations are positive ions, and what happened? They became these cations by losing electrons. So metals form cations. So a potassium atom in a metallic bond would lose an electron and become a positive ion by losing that 1 electron. And a calcium, who has 2 valence electrons, would lose 2 electrons to become the cation of calcium. Now when we're naming these ions, it's really quite simple, and we're going to go over that. In the last session, in fact the first session, we discussed the famous scientist Proust, who discovered that when you have a compound follows the law of definite proportion. That means that if you, for example, if you had a water molecule would have 2 hydrogens for every 1 oxygen. And by mass, they would follow a specific ratio. Now when you classify compounds, there's 2 types of compounds. We have compound type number 1, a molecular compound. A molecular compound is composed of many molecules. And these units that we discussed before that nonmetals will create are made up by joining nonmetal atoms together that are different from each other. They're not the same atoms, they're different atoms. So if you have different nonmetal atoms and you combine them, you will get a molecular compound. If the 2 nonmetal atoms are the same, then you're not a compound, you're an element. So there's a difference. The second type of compound we'll be discussing is made up of cations that are metals. There is an exception to that rule. The famous polyatomic ion, you remember from class, the ammonium ion, which is a non-metal combination of atoms that has a +1 charge. But typically ionic compounds would have a metal ion with a non-metal ion. The cation and the anion bound together by their charges. And the only exception to the rule about metal and non-metal is the ammonium ion. The electrons lost by the cation are gained by the anion. And the difference in charge, the electrostatic Coulombic force, is what keeps those ions together. And it turns out to be the strongest kind of bond you can have. So, what's the difference if we break it down? Well, in ionic compounds, there are what we call the formula unit. That's the combination of the cations and anions in the correct ratio that the charges would add up to equal 0. We call that simplest formula the formula unit, or the empirical formula. That's another term for it. The empirical formula unit is what ionic compounds use. And molecular compounds is made up of molecules. Okay? Key thing, if you have an ionic compound, you're going to see a metal and a non-metal in it. So when you see those Regents questions, which of the following is an ionic compound, you're looking for that metal and you're looking for that non-metal in that same chemical in the formula. When you have a molecular compound, what is always true, and there's no exceptions to the rule, you have only non-metal atoms in the compound. Typically, ionic compounds, there is at STP conditions, which is ice water conditions, all ionic compounds will be solids, guaranteed. That is not necessarily true with molecular compounds. You could have it in gaseous phase, liquid phase, or solid phase, and there's a reason for that, because what keeps the molecules together in that phase is very weak, what we call intermolecular forces. Melting points of these ionic compounds are extremely high. It's very difficult to liquefy an ionic compound. If you took salt from home, put it in a spoon, and put it on an open flame, it would not melt. The temperature of the stove couldn't get hot enough. You'd have to get a blowtorch out to melt an ionic compound. But yet, sugar, which is an example of a molecular compound, would immediately melt in a spoon. That's important. So when you think of ionic compounds, here's a good analogy. Think of rocks. Can you melt a rock? Okay? Well, to melt a rock, you would have to get to extreme temperatures like what's in a volcano, for example. Magma or lava would be an example of melting a rock or an ionic compound. So you're dealing with extremely high temperatures. Versus sugar or ice are examples of molecular compounds. So if you're thinking of properties of molecular compounds, think of sugar and ice. If you're thinking of ionic, think of rocks. Now, we tell people in a molecular compound, for example, molecular compounds have molecular formulas. And the formulas are telling you, we don't write ones in chemistry. The symbol itself counts as 1. If there's more than 1, then we're going to place a number, which we call a subscript, next to the symbol to indicate how many of those atoms are within the molecule unit. So a molecular formula is what is the number of atoms in that single molecule unit. So C6H12O6, we all know that as a form of sugar. This is important. It's telling me that for each unit or each particle that stays intact, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Remember the world of Legos that we started our first session with. We're talking about the Lego itself. What's inside the Lego? When it comes to ionic compounds have formula ratios in the simplest ion ratios possible. So the formula of an ionic compound is based on the charges of the ions. That's not true for molecules. It's only true for ionic compounds. So the charges on the ions in the ionic compound have to add up to equal 0, or it will not stay intact. So every ionic compound formula, this empirical formula, must have the ratio of ions it takes to equal out the charges, positive and negative, to equal 0. Remember that the metals, as a review, are going to lose their electrons and become cations. Group 1 only has 1 valence electron, so they'd be positive 1. Group 2 would be positive 2. Group 13 would be positive 3. Then once you cross the metalloid barrier, remember that the nonmetals, the halogens, are negative 1. The oxygens group, called the chalcogens, that's the correct technical term for it, but you don't have to know that, is negative 2. And then you have nitrogens group, normally we name the groups after the first atom on the top of the column, would have a negative 3. The negative numbers is how many valence electrons they need to get that octet jacket that we talked about in the last session. And these guys have positive numbers, not because they want to lose electrons, but they're forced to lose electrons because the nonmetals are taking the electrons away from the metal, and the metals are shrinking in size when they become cations, and by doing that they become more stable. So you got to keep track of these valence electrons, right? And remember that all they're doing is moving those valence electrons from one atom to another or sharing them among the atoms in the molecules. So what's neat is that on the Regents we have a table that tells us, their periodic table will give us a Bohr electron configuration, and the last digit is telling us how many valence electrons are in each atom. We use symbolisms, the electron dot diagrams that we discussed in our last session, to show us how the valence electrons are moving. So, the electron dot diagram for nitrogen. If you look up nitrogen on the periodic table, you'll find the Bohr configuration. The last digit in the Bohr configuration is a 5. So, what we do for the electron dot diagram, again, this is a review. We write down the symbol, and we're going to place 5 dots around the symbol. Okay, so we add an electron one at a time on each side. This is a great technique because what it will do for us is show us the number of available electrons that nitrogen may need or can use to share with. For example, nitrogen has what we call free bonding electrons. Bonding electrons are electrons that are unpaired in the electron dot symbol. These two here are not typically used to bond with. Okay? Now, if it comes in contact with a metal, in order to get that octet jacket, which is 8 electrons around the symbol, or in the valence shell, because that's what this represents, it needs 3 more electrons to become a nitride ion. What's neat about the Regents? They give us this reference table that gives us, 1, the common oxidation numbers of the atoms. What that means is when it bonds, that's what kind of ion the atom will turn into. So these guys will typically turn into cations, a +1 cation, a +2. Remember, we could have figured that out by the electron configuration. The last digit is telling us how many valence electrons they have. Remember that metals have low electronegativity from our last session, so they're not good at holding on to their valence electrons. Versus these nonmetals, the nonmetals here, now carbon is kind of along the border. It can either lose 2 or 4 electrons in a covalent bond. So in other words, if it bonds with other nonmetals, it's going to typically, its valence electrons would go onto the other nonmetal with the higher electronegativity rather than stay on the carbon. That's what the positive numbers are telling us. But a typical nonmetal comes in contact with the metal, it's going to draw electrons. So carbon will like to turn into carbide ion if it comes in contact with a metal. Oxygen wants to become oxide with a -2 charge, and fluorine wants to turn into fluoride with a -1. Neon and helium, they don't turn into any ions because they're noble gases. So you need to be able to immediately draw Lewis dot structures. So I'm going to show you how it's done. So if we want to draw the Lewis dot structure for sodium, we would go with, let me use a black marker. Sodium has 1 valence electron. How do we know that? Well, we look at its Bohr configuration, there's a 1. So therefore, there would be only 1 dot. So that's what sodium would look like. Again, this dot is just to point it out. So if we want to draw this, I'll draw it again, Na with 1 dot. Right? So that's this Lewis dot structure. And if we wanted to draw the symbolism for its ion, the cation, you remove that electron, and now you tell somebody it has 1 more proton than electrons in the cation, and that would be the symbol for the ion. Now, when we have metals, just to let you know, we typically like to use X's for the valence electrons. It's a better technique, and we'll show you why we do that. And if we go to the next atom, which is magnesium. Magnesium, you write the symbol. How many valence electrons does it have? Well, you look at that Bohr electron configuration, there's a 2. So you put, again, an X instead of a dot. You could do that. And if you wanted to write what is its symbolism for its cation, it would be Mg losing those two X's, which are the valence electron with a positive 2 charge. Plus 2, 2 plus, same thing. Okay, the next one, carbon. Well, carbon has 4 valence electrons. Carbon's a nonmetal, so we're going to use dots. I like to put 1 on each side because it tells me that carbon can form a maximum of 4 bonds. If it becomes a carbide ion, what will happen, not only will it have its original 4 dots, but typically it's going to take electrons from a metal, and what you can do is put X's as the electron that it took from those metals, and then you place the ion in a bracket, and you put the charge of the ion in the upper right hand corner. So that would be like a carbide ion. The next atom would be oxygen. Oxygen, again a nonmetal, has 6 valence electrons based on the periodic table they gave. So I go 1, 2, 3, 4, 5, 6. This indicates that oxygen is looking to form 2 bonds or gain 2 electrons from a metal. If it was to gain those 2 electrons, again we place the 6 original dots and place X's that symbolize the electrons it gained. So I would have to have a negative charge for every negative electron that it gained. And then if we want to draw fluoride, fluoride has 7 valence electrons. So fluoride would be 1, 2, 3, 4, 5, 6, 7. And if it is short 1 electron to become a fluoride ion, again we write down the 1, 2, 3, 4, 5, 6, 7 electrons it had originally, and then we place an X to indicate the electron it gained. So this is the Lewis dot symbolisms for the atoms. Again, metals you can use X's, non-metals you can use dots. And this is the Lewis dot structures for the ions, which the Regents loves to ask questions on. Now the noble gases, they don't produce ions. But they might ask you to draw their Lewis dot symbols. So neon, the noble gas that has the octet jacket. So neon would be Ne, and then you place the dots. 5, 6, 7, 8, and that would be the Lewis dot structure for neon. And helium, which is the only noble gas that doesn't have 8 electrons, it only has 2. But we don't separate the dots because it doesn't form bonds. We keep the dots together. So you need to be able to draw the Lewis dot structures for atoms. And the way you do it is you look at the number of valence electrons they have. Really simple. Okay? So we'll close our whiteboard here, hopefully. And we will continue. So, remember that metals lose their valence electrons. That's how they react. So when they lose their valence electrons, as a reminder from last session we had, they lose their valence electrons and they shrink in volume. And by losing their valence electrons and shrinking in volume, they become more stable for 2 reasons. One, now when it's, for example, sodium loses its 1 valence electron that's in its outer shell, and now it has the exact same configuration as a noble gas. 2-8 is the noble gas listed above on the row above the original sodium atom on the periodic table. So by shrinking and now creating these 8 valence electrons that are really close to the nucleus, it's not going to react anymore. So that's why metals end up becoming more stable when they turn into cations. And in the last session, we discussed the smaller the cation, the more stable it is. So, calcium. If you were to take out your periodic table and look at the centerfold that they give you, you'd see the periodic table. you can find calcium. Ca is for calcium. You can see that its Bohr electron configuration is telling you it has 2 valence electrons. And it's also telling you what kind of ion does calcium want to turn into. The calcium cation has a +2 charge. So calcium, if you drew the Lewis dot structure for it, 1 dot, 2nd dot, if it becomes an ion, it's going to lose those electrons. Now, it doesn't want to lose those electrons. It's being forced to do that by some other atom drawing them away. That's important to note. But when that happens, and they lose those electrons, and it becomes calcium with a +2 charge, it's going to shrink, become more difficult to take electrons away. Therefore, it becomes more stable. So when something starts out less stable and then becomes more stable, energy is released. That's important to know. So when these metals lose their valence electrons and become these ions, they're becoming more stable, so energy is going to be released. The nonmetal anions are created by the nonmetals gaining enough electrons to create this jacket, called the octet jacket, in its valence shell. Once you place those 8 electrons around the nucleus, you kind of create a field of negative around the nucleus is positive. And now, all of a sudden, the volume of the atom gets much larger. So when a nonmetal gains electrons, it becomes an anion with a volume much larger than the original atom. And that makes it more stable. That's important. So sulfur, for example, has 6 electrons in its valence shell. It's too short. So it wants to become a sulfide ion with 2 more electrons and a much larger volume. So sulfide is going to be larger than a sulfur atom. When that happens, sulfide is much more stable than the actual sulfur atom. Now it has the exact same electron configuration. There's a term for it. It's isoelectronic, means it has the same electron configuration as a noble gas. So, here's phosphorus, a typical nonmetal atom. Again, I go here and I see it has 5 valence electrons. So I put 1 dot, and then I come around, and now I notice there's 2 dots together here, and these dots are by themselves. And that's important. That immediately tells you 2 things. If this nonmetal atom comes in contact with a metal, it's looking to draw from the metal 3 electrons. It wants to have pairs of electrons in these locations. It also tells you a second thing. If it comes in contact with another nonmetal, the only electrons it typically would share are these unpaired electrons, which we refer to as the bonding electrons. So it tells you 2 things, and that's why these electron dot symbols are so important, and that's why we're using this review session to go over it. Now, if you look at the periodic table, you see some interesting numbers up here. The -3 means that is the common anion that phosphorus atom will turn into. So phosphorus, when it becomes phosphorus with a -3 charge, it's not phosphorus atoms anymore. It's called a phosphide ion. That's what happens. So, and an ion would have -3, meaning it would gain 3 electrons from some metal. So that number on the top right, the negative number, is telling you what it would do if it comes in contact with a metal. It also, you notice there are other numbers, positive numbers, which do not make sense because nonmetals typically want to become anions. The positive numbers are telling you how many electrons will it possibly use to form what they call covalent bonds with other nonmetals. And we already know these are the 3. So that +3, that's what it's telling you. But it also tells you it's possible that it can use all 5. How do you know that? By that +5 number there. And it's telling you if it comes in contact with a nonmetal with higher electronegativity, these electrons will typically be on the other atom with the higher electronegativity. That's what the positive numbers are telling you. So these negative valence electrons it have would stay on the other nonmetal most of the time. So it's telling you a story about even the covalent bonds it would form. So nonmetals have a certain number of valence electrons. It will look to gain to fill that outer shell. So this would happen if it comes in contact with a metal. it will take the electrons away from the metal and become what we call a phosphide ion. Now, when you draw a phosphide ion, you don't leave it that way. Okay? Again, I'm just reviewing how you draw the ions. For phosphide, you want to show the original electrons that it has. So originally it had dot here, 2 dots here, a dot here, and a dot here. And then typically what you would do, the electrons it gains, you put X's, like so, and then you place the whole thing in a bracket, and the -3 is on the outside of the bracket. That's the symbolism for a phosphide ion. That's how it works. Again, why use X's? Do you have to use X's? No, you don't. But if you had to draw them, and they're showing the metal ion with the negative ion, the anion, the X's would indicate that those electrons came from the metal. They weren't originally on the phosphide. And the Regents loves to draw ionic compounds. Remember that the reason why the nonmetals are gaining electrons is they want to get to look like an argon or Lewis dot structure. Right? This guy has 8 in its outer shell. The term ionic bonding refers to the attraction between the ions that are created between the metal and the nonmetal, or the metal and the polyatomic ions, which we'll talk about in a minute. These ionic compounds are sometimes referred to as salts. A salt does not have H+ ions in it and doesn't have OH ions in it. All salts are ionic compounds. So you might see the word salt substituted in for the word ionic compound. Remember that ionic compounds are following a formula unit, which is basically telling you how many of those ions are present. So, NaCl, the classic salt you learned in the 4th grade. Because every time you hear the word salt, your teacher's talking about NaCl. It turns out there's billions of salts. This is one of a billion. And it's an ionic compound, because it means the same thing. So here's your sodium atom with its 1 valence electron. Here's your chlorine atom with its 7. Right? And I knew this because I had this on my periodic table. I could look at the last digit in the Bohr configuration. Right? But now I know that this chlorine atom wants to turn into a chloride with a -1 charge, and this sodium atom wants to become a sodium ion with a -1. Notice that the nonmetals always change their name when they turn into an ion. We always end their name with an "ide." And these guys don't really change their name. I called it a sodium ion. Right? So this valence electron is going to get drawn away and go on to the chlorine. And now you have the ions. Right? You got the sodium ion in contact with the chloride ion. This is the unit right here. And the way we write the formula would be NaCl. We don't put the charges. We don't leave the charges in the formula unit. So I got NaCl as the formula. It's understood that it's an ionic compound and it has ions in it. What about this situation? I have calcium atoms coming in contact with phosphorus atoms. So based on last week's presentation, our last presentation, these electrons are going to be drawn to the phosphorus because the phosphorus has a higher electronegativity. Therefore, it can draw the electrons away. This guy has a low ionization energy and a low electronegativity, so it has no choice. When these atoms touch each other on the surface of their elements, you're going to get a chemical reaction if there's enough activation energy present. The activation energy is being used to release these electrons. That's what's happening. So, those electrons are gone. But wait a minute. Phosphorus needs 1 more. So just having 1 calcium ion with 1 phosphide ion is not going to work, because the phosphorus needs more. So the phosphorus is going to have to interact with another calcium atom. So now what happens, this one electron is enough for that one phosphorus, but you can't have partially reduced, a partial ion like that, because the calcium can't have just one valence electron and the other one gone. So now this is satisfied, this is stable, and this is not. So what has to happen? Another phosphorus has to get involved and draw that electron away. Once that happens, this is stable, but that's not. See, it's like pieces of a puzzle have to fit. So if these calcium ions come in contact with phosphorus, they have to create the correct number of ions that will make the charges cancel out to equal 0. So this phosphorus searches for another calcium to draw electrons. And it works out. Now, if this electron goes here and that electron goes there, I'm going to have the correct ratio of ions that will add up to equal 0. Because you can't have an ionic compound unless the ions add up to equal 0. So a plus 2, a plus 2, a plus 2 gives me a positive, plus 2, plus 2, and plus 2 gives me a positive 6. Awesome. What did you think? I was going to ask questions? And a negative 3 and a negative 3? Negative 6. And we learned in algebra, I think, right? Or way before then. A positive 6 and a negative 6 will cancel each other out to equal 0. Now, this is what a Lewis dot structure of an ionic compound looks like. This is what you would leave up there. So if they said, draw the Lewis dot structure for this calcium phosphide, right? This is what you would put on a piece of paper. Remember that I have brackets. The correct thing is brackets around here, right? Because the whole thing is charged. And then they would come together. Now, how do I develop a formula? Right? Well, the formula basically just counts up the particles. How many of these? 1, 2, 3. How many of those? 1, 2. So how do you do that? Well, you write what they call an empirical formula. Right? So I had 3 of these calcium ions and 2 of those phosphides. You do not put the charges on the top. Because whenever you put charges on an ion, that means it's floating around in water. And that's not true right now. This is a solid. Ionic compound typically is a solid at STP conditions. So this is the formula unit that for the calcium phosphide Lewis dot structure that I had a few minutes ago on the screen. This is telling me, I know this is ionic compound, so this is a positive ion, this is a negative ion, this is the subscripts are just telling me the grand total necessary to create that charge of 0. That's how it works. Students struggle with this. Students struggle with this. Now we're going to get involved here. Typical, simple, straightforward Regents question. It says, which Lewis electron dot diagram represents the bonding in potassium iodide? So which choice? So with your hand, put up a number that you believe is the correct choice, the correct drawing. So whoever hits a vote. And then I'll just say what the majority says, or if it's split. All right, you ready for a vote? It's okay to be wrong. Okay, so we have a split. So what's the correct answer? 1, this is an ionic compound. So you want to write this down. This is very important. If it's an ionic compound, and I'm drawing a Lewis dot structure, I got to have ions in my structure. So let's work backwards. This can't be right? Because the metal loses its valence electron, so that can't be right. And 2, there's no charges written down. When you draw the Lewis dot structure, there's supposed to be charges. This can't be right because there's no charges shown. This can't be right because metals don't form anions. That can't be right. So now I'm left with this guy, which is the correct answer. So this represents the potassium atom that lost its valence electron and became a cation. And this represents the iodide ion that gained the electron from the potassium that is now a -1. And I know I'm right because if I go to my periodic table, this has a +1 charge and this has a -1 charge written on the Lewis dot structure. You have to have that in order for it to be correct. Okay? So, let's continue our review. It says when a potassium atom reacts with bromine. Remember, potassium's on the left side of the periodic table is a metal, and bromine's on the right side of the periodic table. It's a nonmetal, right? So potassium, what's going to happen to the potassium atom? Oh, you're going to have a vote. I'm not going to continue until you have a vote. Just put up a finger and tell me which one. Okay, so now here's the thing. Potassium only has one valence electron, right? So what's going to happen when it reacts with bromine, it's going to become a potassium ion and lose its sole one valence electron. That's how simple it is. You do need that periodic table in front of you at all times, like a weapon, right? Or it's going to be a tough one, right? Then he says, okay, when metal atoms bond with nonmetals, the nonmetal atoms will do what? It's okay to be wrong. Just vote. I'm not going to single you out. I'm just going to. Hey, don't hesitate. You got to say, okay, the nonmetals. What do nonmetals do when they come in contact with a metal? That's why I kind of reviewed it. So give me a vote. What letter? Right? Well, the nonmetal is going to gain electrons, so that means it's either A or C, right? And then the next thing would be, what happens to the nonmetal atom when it gains a negative charge? Does it shrink or does it increase in volume? It's going to increase its volume. So the nonmetals always get fatter. I don't like to use the word fat, but that's how I memorized it. They always get fatter. They always increase in volume when they become an anion. Metals shrink. That's how it works. Okay? It says an ionic bond forms between atoms of which combination of atoms would create an ionic bond? The majority says it's potassium and chlorine, and you are correct. Because potassium's a metal and chlorine's a nonmetal. It's really that simple. The only exception to that rule is the ammonium ion. The ammonium ion, NH4+, is a positive ion. That's the only exception in an ionic compound that could exist as a positive ion. All the other cases, there's always a metal. There's always a metal. Right? Which compound contains, now this is unique, because we didn't discuss covalent bonds in this session, but one of these guys has ionic bonds, right? And it also has covalent bonds in it. And you guys know the answer. The majority says it's choice 1. Because if it's ionic, there's got to be a metal in the formula. These guys, well, wait a minute. This is an ionic bond too, right? But this has what they call the famous polyatomic ion in it. And inside the polyatomic ion, there's covalent bonds, right? And we're going to kind of go over that in a minute. Which compound is ionic? And we're going to get better at this. Got a vote back there? Okay, so let's look at it. Ionic. I'm searching for a metal. This guy doesn't have any metals in it. This guy doesn't have any metals in it. This guy doesn't have any metals in it, but this guy does. So as soon as you see a metal, right, in the compound, connected to some other atom, it's ionic. It's ionic. Okay? Now this is a little different. This one says, which electron dot diagram has both an ionic bond in it and a covalent bond in it? Boom! Majority wins. They say it's this guy right here. Because it's ionic, so there's the metal ion. That's got to be the right answer, right? But wait a minute. This guy's a metal in it too. But again, this has the unique polyatomic ion in it. And what's keeping these oxygens connected to the sulfur to generate this ion are actually covalent bonds. So again, these are the tough ones. Okay? And then this value actually would follow it says which compound contains both covalent and ionic bonds. Well, you would have to know that the ammonium ion is a polyatomic ion. So ammonium chloride, okay, that's a little tricky because there's no metal in there. Because ammonium is a unique positive ion. It's one of the sole positive ions you need to know that's not a metal, is ammonium. Now, remember in the session in the beginning I says when you think of ionic compounds, think of rocks. You want to write that down. Ionic compound, rocks. Molecular compounds, ice and sugar. That's how you do it. Ice and sugar. So, rocks. They have crystalline structures. They're as hard as a rock, right? They're hard to break, but if you hit them with a hammer, they'll crack. That's important. They will crack. Some rocks can dissolve in water. Some rocks don't dissolve as well, right? How do we know rocks dissolve in water? Erosion. So therefore, some ionic compounds will dissolve in water, and some don't dissolve as well, right? But over time, they will dissolve. The structure is going to be rigid. To melt a rock, you have to put it into a volcano. That's extremely high temperatures. So they're going to have extremely high melting points because the attraction between the positive and negatives is so strong. It's the strongest force in chemistry. We call it electrostatic Coulombic force. It's the strongest bonds or ionic bonds on a per bond basis. It's important to note. In college chemistry, we know the smaller the ions, the stronger the ionic bond. So that's why the size of the ions that we discussed last session was so important. So they're going to ask you simple questions like, the arrangement of particles is most ordered in a sample of what? Well, wait a minute, they're all NaCl. What does NaCl AQ mean? It's dissolved in water, right? So you have sodium ions floating around and chloride ions floating around. That's what that means, right? The little script L means it's a liquid. The G means, wow, you were able to get that gas not beyond the melting point and then got it to the boiling point. Now it's in a gaseous phase. You're talking in the thousands of degrees to do something like that. And then you have NaCl with a little S. The S is basically telling you that the crystal is formed, right? So which one is the most ordered? What choice? Choice 4 is correct, right? So when they say crystalline, this is what they're talking about. There's a pattern, right? Now what's important, this is NaCl, for example. This is Na, this is Cl. How do I know this is Na? It's smaller in volume, right? Because that's what they do, they shrink. And this is Cl, it's bigger. But what you should know, this Na doesn't know if it's really hooked up to this Cl, or it's hooked up to that Cl, or it doesn't really know that. So when it forms these crystals, you really have billions and billions and billions of these ions, all stacked. But the unit that's repetitive is 1 Na for every Cl. That's why its empirical formula is NaCl. It's telling you what's the repetitive unit throughout the whole crystal. Now, what's interesting, these ionic compounds don't conduct electricity when they're in a solid phase. But if you're able to melt them at these high temperatures, the sodium ions could gain an electron if you force them to, and the Cl chloride ions could lose an electron if you force them to. So you could force them to conduct the electricity in the liquid phase because the ions are mobile. And it will also conduct electricity if you put them in the aqueous phase, which you dissolve them in water. Because pure water doesn't conduct electricity, believe it or not. It's not like in the movies where they, when someone gets electrocuted in the bath water, that's not pure water. That's water with salts dissolved in it. So that's why typically human beings, even we have salt on the surface of our skin, if we go into the water, we immediately make the water impure. We add more ions to it. Now you can conduct electricity because the positive and negative mobile ions will be able to draw electrons from the electricity you try to put in it. So that's when these things can conduct electricity, when it's in a liquid phase or it's dissolved in water. Now you say, why are they brittle? Well, if you generate enough force on the surface of the ionic compound, you could force this positive ion to be pushed, and it would sense the other positive ion, and it would repel. That was like in our first session, we talked about positive and negative charges are attracted to each other, but if you force a positive next to a positive, it would repel. So if I pushed hard enough, I could get them to repel, and it would crack. That's important to know. So, here's some more review questions. What type of bonds are formed when metal atoms combine with nonmetal atoms? Choice is, we gotta get quicker at this. Choice number 2 is correct. Next, a substance has a melting point of 1074 Kelvin. Conducts electricity only when you dissolve it in water, not when it's in the solid phase. The substance is most likely a, choice 4, ionic solid. Atoms of nonmetals generally react with atoms of metals by, what do nonmetals do? What do you say? Just give me a number. Okay? So, nonmetals will gain electrons because that's what they do. Right? So they'll gain electrons. And once they gain electrons, what will happen? They will bind to the metal that lost the electron, right? And form an ionic bond. When ionic bonds are formed, what do metallic atoms do? I'm going to get it in there. When ionic bonds are formed, metal atoms tend to what do you vote back there? Just give me a letter, the number on your hand, and I'll correlate it with the letter. Okay, so metal atoms tend to lose their valence electrons. That's a fact. And they shrink and become positively charged because now they have more protons and electrons total. That's what they do. Right? They become cations with a positive charge. And then they bind to the nonmetal that took their electrons that now has a negative charge. The elements lithium and fluorine combine to form an ionic compound. Okay? The electron configurations in this compound are the same as the electron configurations of atoms in group. Well, wait a minute. What do you mean? So when this guy combines with fluorine, what does lithium going to do? It's going to lose its valence electron. And now its electron configuration that's left over will look like what group on the periodic table? When it loses its valence electron and shrinks, it's going to have the same electron configuration as which group? Which group? Now think about it. Let's go to the nonmetal side. The nonmetal is going to gain electrons. How many is it going to gain? To get the magic 8. Which group? All of them have the magic 8. Noble gas group, right? That's the last group on the periodic table. The last column has a number. It's number 18. So when these guys lose their valence electrons, they're going to end up having the same configuration in one of the noble gases. The nonmetal, when it gains the electrons, will end up having the same electron configuration of a noble gas, which are all located in group 18. That's how it works. Now, how do we name these ionic compounds? Okay, how do we name these ionic compounds? The name of an ionic compound always starts with the name of the cation first. Now, what's cool about the cations? They take the name of the atom. Okay? If the cation that it becomes, on the periodic table, it tells you what the possible charges of the cations are for that atom. If there's more than one number possibility, then you're going to have to tell somebody which one you're working with in this ionic compound by using a Roman numeral to represent the charge of the cation. Again, the Roman numeral tells you what charge the cation has. And typically these are the metals that are in the middle of the periodic table, called the transition metals, because they have multiple possible oxidation states. In the last session, we talked about why. Not only does it lose its valence electrons, but it could also lose some of its core electrons located in the d orbitals. So there's more than just the valence electrons they could lose. That's why they're called transition metals. They kind of are stuck in between. Not only do they lose their outer electrons, but they could also lose some of their next core electrons right underneath the valence electrons, which are located in what they call the d sublevel. So they're unique, and that creates a problem because now you got to tell somebody which transition metal ion you're working with. And the way you do it is you give the name of the transition metal and what charge it has with a Roman numeral in its name. There are also p-block metals. Those are the ones close to the non-metal side that have multiple oxidation numbers. So you got to tell somebody which one you're working with this Roman numeral. So here's an example of transition metals right here, right? Here's a transition metal. Here's a p-block metal, which is to the right of the periodic table. They have more than one number in the box. So if I wanted to tell somebody I'm working with iron with a +2 charge, I got to write down the word iron, parentheses with a Roman numeral 2 in it, versus iron with a +3 is iron with parentheses with a Roman numeral 3. This guy here is lead. Lead has two possibilities, a +2 or +4. So in the name you got to use those Roman numerals. So here we go. Let's see. What's the name of this ion? Real simple. It takes the name of the atom. So this is a sodium ion, right? So it would be called sodium, just like the atom. This guy would be called calcium ion. This guy would be called an aluminum ion. These metals only have one possible oxidation number in the little box on the periodic table. So you don't have to worry about the Roman numerals. But when you get to this guy, that's a problem. So if I look up iron, I see it has two numbers. So I have to tell somebody that I'm working with iron, Roman numeral 3, right? And if I go with this guy, I got to write down iron, Roman numeral 2. This guy, again, has two possible oxidation numbers. There's two different lead ions. So this would be lead with a Roman numeral 2 in parentheses. This guy's in group 1. No multiple possibilities. So it's just called lithium. So here's examples of using the words. Now we're going to say, okay, what's the formula? A potassium ion is K plus, right? A magnesium ion is Mg with a +2, right? This guy has a Roman numeral. That means there's more than one possible copper ion. This is copper with a +2. This guy has like 4 different options. So this is chromium with a +6. You got to know your Roman numerals. Barium doesn't have more than one possibility. So it's barium with a +2. But mercury does. And this is mercury with a +2. That's how it works. Now the anions, if there's only one kind of atom, one type of atom is in the anion, then it's real simple. You take the name of the atom that created the anion and you take away the "ine" ending and you put "ide" in its place. So fluorine turns into fluoride. There's a big difference between those two things. Do you brush your teeth with fluorine? No, because if you brush your teeth with fluorine, your face would fall off. That wouldn't work well. But you brush your teeth with fluoride, which is the anion of fluorine. So there's a big difference in the name. So if I say, hey, there's a fluorine atom, we better leave the room because there's going to be a chemical reaction with me. That's bad. But if I say, hey, there's fluoride in that toothpaste, it's okay. It's okay, we don't have to leave. I can brush my teeth with it. But I also have to be aware if I brush my teeth more than 3 times a day, I could have a problem. I could actually, the fluoride is still relatively unstable because it's really small. And anions that are really small are still reactive. That's why we brush our teeth with fluorine, not with iodide, for example, which is much larger. So this would be called chloride, right? This would be called, what would you call that? N with a -3. Nitride. And what about that guy? Bromide. And what about that guy? Oxide. Very good. See? Piece of cake. What's the formula for a sulfide ion? Well, that's easy. I look up on periodic table. I know it came from sulfur, so I write the S. And then I look at its oxidation number. It's -2. Right? Iodide is iodine. Right? I look on the upper right-hand corner. I see a -1. I with a -1. Phosphide, that's phosphorus that we showed you before, right? It has a -3 on the top in the little box with the oxidation state numbers. That's what they're called. And the strontium ion is a metal ion with a +2. So, when you write the name for an ionic compound, you take the formula and always take the first element and say, what ion is that? But here's the thing. I got a transition metal here. And transition metals have more than one oxidation state. So which one am I working with? To figure that out, you actually have to rely on the nonmetal. Non-metal only has one negative oxidation number in its box. So you go to the nonmetal, you look in the box, and you see that sulfur has a little -2 next to it. Then therefore, why must there be 2 copper ions hanging out with one sulfide ion with a -2? That would mean that each copper has to have a +1 because there's 2 of them, right? So 2 times a +1 would cancel out the -2. So the ion that I'm working with here is a copper Roman numeral 1. So you name the cation first and the ion last. That's how you do it. So you see, we had to figure out what charges are these copper ions by looking at the nonmetal first, because the nonmetal will only take one negative oxidation state. So here's another situation like that. Here's iron, a transition metal. There's more than one possibility of what ion I'm working with. So I go to the anion, and I note there's 3 of them. And oxygen has a -2 charge. That's its only option when it's an anion. So 3 times a -2 gives me a -6. So there's 3 of these -2 ions, if you can picture them like we had the drawing before. And there's 2 of these positive ions that cancel out the -6, right? So what charge must the iron have that will give you a +6? So each one, right, has to have a +3 charge because there's only 2 of them, right, to cancel out the -6. So I'm working with iron 3 oxide. See, in order to have an ionic compound, the charges have to cancel each other out. Now, your teacher might have showed you some tricks. You know, there's always tricks and analogies and acronyms. But to understand it, you got to understand it's like a puzzle. The puzzle pieces have to come together to cancel out the charges. Now, someone mathematically inclined, right, can vision that. If you're not mathematically inclined, you also could know what they call the crisscross method. Like, where did this 2 come from? And where did that 3 come from? Well, if this is a -2, see the similarities? If this is a -2 ion, which they don't write the charges, I have to envision that. That's where that 2 came from. And this has to be a positive 3, because that's where that 3 came from. That's where the crisscross method that your teacher might have showed you. But that's only true when the charges are not the same. Can you use the crisscross method to figure out what those subscripts are going to be? It's better to understand the puzzle and the puzzle pieces that are necessary. This means there's 3 oxide ions in the puzzle that are going to be canceled out by 2 plus 3 puzzle pieces. They come together to give me 0. That's how it has to work. So when you have only 2 types of atoms in your formula, sometimes we refer to those as binary ionic compounds. Only 2 types of atoms. So here we have a sodium atom and chloride, a sodium ion and a chloride ion. There are only 2 types. So we call those binary. Now, if you have 2 of one type, it's still only 2 types. So magnesium bromide, which is this compound, is also a binary ionic compound. What do you mean binary, Mr. Langell? There's only 2 types of atoms involved. When you get to more complicated ionic compounds, you'll note, like those polyatomic ions, there's more than 2 types of atoms involved. And those transition metals, those are the ones with those possible oxidation states, so you have to be aware of the Roman numeral system, right? So, here's another example, CuO. Which copper ion am I working with? Well, if oxide is always -2, that's what's in the little box, it's its own sole negative number, then if I only got one Cu, that's got to be a +2 in order for the puzzle pieces to come together. If I got copper 2 chloride, what would its formula be? Okay, for copper 2 chloride. This would be like a short answer question. You know, what is its Lewis dot structure for copper 2 chloride? Right? That could be a Regents question right there in the free response section. In short free response sections. So if I wanted to draw the Lewis dot structure for copper 2 chloride, copper with a +2 charge, chlorides, I go in the little box on the periodic table, look at the upper right hand corner, chlorides have a -1 charge. Is this going to work? Is this going to work? The answer is no, because it's a +2 and only one -1. You can't have that. I'm missing a puzzle piece. What puzzle piece am I missing? What do you say? What should I put up there? Do you want me to put another copper +2 or another chloride to make the magic happen? Very good. Because if I put up another chloride, -1, -1 gives you a -2. That cancels out a +2. Boom! I got an ionic compound. How do I write that formula? Real simple. You write the symbol of the positive ion and write down how many you have. But we don't write ones in chemistry. It's forbidden. We don't write ones. The symbol counts as 1. But the chlorines, I have 2 puzzle pieces. So I put a subscript in for the puzzle piece. And that's the formula of copper 2 chloride. That's how it's done. Again, those transition metals are tricky because there's possible more than one oxidation state. So they got to give me information to figure out what is the oxidation state of the transition metal. So someone says, okay, name this guy. Well, a bell should ring in your head if you notice that the metal is a transition metal. So that means I need a Roman numeral. It's really that simple. But what is the Roman numeral? Well, it depends on how many of the negative pieces I have, right? I got 3 chlorides, and chlorides have a -1. So the oxidation state of this sole one positive piece has to be a +3 to cancel out the 3 -1s. right? So in the name, I have to tell somebody, listen, this is cobalt with a +3. That's what the Roman numeral means. Linked to those chlorides. That's how it works. So, what's the names of the following compounds? So what's the name of this guy? What do you think?
Potassium chloride.
Potassium chloride, absolutely correct. What's the name of this guy?
Sodium nitrite.
Very good, sodium nitride. What's the name of, now we're going to get tricky. You know it's going to get trickier, right? Now, what's the name of this guy?
Lead to
Oxide, very good. Lead, Roman numeral 2 oxide, because there's two possibilities. Which one do I have here? This is lead with a +2, because it's being canceled out by only one oxide piece, which is a -2, right? What about this guy?
lead 4.
Very good. Lead, Roman numeral 4 oxide. See? It comes back to you. It comes back to you. What's the multiple choice question going to look like? Here you go. What is the formula for a compound that forms when magnesium bonds with phosphorus? So what do you need to figure out? Well, I need to get my periodic table out, right? I'm going to tell you, magnesium has a +2, and that's the sole number, and phosphide has a -3. Again, magnesium has a +2. Chemistry is like a Batman episode. You always have to have your utility belt, which is your period, your little reference table. So magnesium is a +2 piece. And phosphide, again, I know it has 8 electrons now because that's what happens to them, is a -3 piece, right? So if we're playing with puzzle pieces, how many magnesiums? So you say to yourself, this is where the mathematician comes in. What number is 2 and 3 divisible into? Lowest common number. I think it's 6, right? So how many of these do you need to get a +6? 3, right? So I need 3 of these. How many of these pieces do I need to get to have a -6 total? 2. Very good. Again, going to the puzzle pieces is the best way to handle this. And you have 3 hours to take this test, so there's no rush. You can stay there for 3 hours, and you really don't need the 3 hours. So you could draw whatever you want on the scrap paper, and then you say, okay, if I draw the formula, how many of these do I have? 1, 2, 3. How do I do that? Mg with a little 3 next to it. How many of those I have? 1, 2. So you come up with your formula. Mg3p2, which is choice A. Okay, let's go to the next one. Sodium is a +1 piece, and oxide's a -2. Now I'm not going to draw the Lewis dot structure. Which one would work? Which choice? Choice 1 is correct. See, you're getting it, right? And now let's look at question 7. Iron 2 sulfide. Okay, so I got iron with a +2, and sulfide on my periodic table has a -2. Which formula would work? Choice 1 is correct. The majority says it's choice 1. See? It takes practice, and sooner or later it all comes back to you. But that's how you deal with the ionic compounds and the ionic formulas. Now these polyatomic ions, you get a list of these polyatomic ions. What's important to know, what I would do on my reference table, is immediately write they have covalent bonds in them. The majority of them have covalent bonds, except like mercury 1. Obviously, there's a metal ion, so it doesn't have that. But everybody else, right, have covalent bonds built into the polyatomic ion, inside them. So the combination of these metal, nonmetal, or nonmetal, nonmetal created these polyatomic ions that have negative charges, and there's some positive ones too, like ammonium. There he is. You don't have to memorize it. That's what's neat about the Regents. There's very minimal memorization. It's all about understanding. So these ions can combine to form ionic compounds, right? These are not going to form binary compounds because there's more than one type of atom in it. So guys like this is sodium, the positive ion, and then you would name, once you see that after the metal comes more than one nonmetal, it's a polyatomic ion. So to get the name, you have to go to the table, unless you memorize them all. So you have to go to the table. So this would be sodium connected to a NO3 with a -1 nitrate, right? This is calcium connected to SO4. I go to the table, SO4, sulfate. So you do it. Uh-oh. There's a transition metal. Ding! Wait a minute, it has more than one possible oxidation state, but there's only one puzzle piece connected to this guy, sulfite. SO3 is sulfite. And it has a -2 charge, so what charge does the copper have to have? It has to be a +2 charge. So the name would be copper, Roman numeral 2, sulfite. You have to have the Roman numeral next to those transition metals or it's wrong. And this is unique. There's that famous ammonium ion, right? There's more than one. This is the only thing you have to remember that's not a metal, is this ammonium. And it's on the polyatomic ion. So this is an ionic compound, even though there's no metals in it. Because you got this famous ammonium ion connected to the famous oxide ion. Why is there two of them? Because ammoniums only have a +1 charge. So it takes two of these to hang out with one of those puzzle pieces. That's how it works. So now that I gave you this quick review, what is the chemical formula for ammonium sulfide? Choice 1, very good, is correct. Doing a good job. Then it says, okay, this is from our last session. Shucks. In our last session, well, actually, we're gonna go back to, let's skip this one for now. Let's go to 2. Which substance is the best conductor of electricity? Choice 3, very good. Liquefied ionic compound. When potassium reacts with bromine, now notice these are, I stuck some repetitive questions in there to see if you recall and you learn from your mistakes, right? So when potassium atoms react with bromine, what will the potassium atom do? Potassium is located in group 1 of the periodic table. Very good. It will lose its one sole valence electron. It says when metal atoms bond with nonmetal atoms, the nonmetal atoms will. What do nonmetal atoms do? Those are the guys on the right of the periodic table with the higher electronegativity. Well, they're going to gain electrons, and they're going to get fatter, right? So they're going to get larger. An ionic bond forms between atoms of? Very good. A. Which compound has both covalent bonds and ionic bonds? Choice 1. What is the formula for sodium perchlorate? Oh no, I would need my polyatomic ion table, right? So let's go back and look at perchlorate. So if we go back a couple of sides, I look for perchlorate. Oh, there he is. ClO4 with a -1 charge is perchlorate. So if we go back, sodium perchlorate, ClO4 is what I'm looking for. There he is. With one sodium, because they cancel each other out, +1 and -1, right? Which is the formula for chromium 3 oxide? Oxide is oxygen that became an anion with a -2 charge. Again, without my help, can you figure it out? Okay, choice 1 is correct. Again, this is a -2, this is a +3, so the common number is 6, right? So 3 -2's will give me a 6, and 2 +3's will give me a 6. That's how I know 1 is right, right? That's how you do it. What is the formula for sodium oxalate? Now, how do you know you're dealing with a polyatomic ion? There's something common here. If you ate it, it's a polyatomic ion, and if I ate it, it's a polyatomic ion. So ates and ites in the negative ion name are always polyatomic ions. So sodium oxalate, I got to go back to my table. Oxalate, I look for oxalate. I scan the table and I'm looking for oxalate. Where is he?
The first one.
The first one right over
The left.
to my left. There he is, C2O4 with a -2 charge, right? So if I go C2O4, oh, there he is, C2O4. So that has to be the right answer, right? Because it's the only one with that polyatomic ion in it. That's how simple it can become as long as you know ate or ite is a polyatomic ion, right? Iron 3 oxide. Oxide's a -2. What's the right answer? Choice 3 is correct. See, we're getting good at this. What is the formula for calcium cyanide? Now, there's no anion from the periodic table that has the word cyanide. So this is an exception to the 8-ite rule, unfortunately. So cyanide doesn't make any sense. It doesn't come from the periodic table. So that means I got to go to the polyatomic ion table and see if it's on there. And if I scan, there's cyanide, Cn with a -1 charge, right? So Cn with a -1 charge connected to a calcium with a +2. Here's another important thing. When you have more than one polyatomic ion, you have to put the polyatomic ion in parentheses in the formula. So this guy right here is the correct answer, because it takes 2 -1 cyanides, puzzle pieces, to connect to 1 calcium ion. Notice some students might pick this one. What's wrong with that choice? This is saying there's 2 nitrogens, not 2 cyanides. So when you have more than 1 polyatomic ion, you have to put it in parentheses and put the number of the puzzle piece subscripts on the outside of the parentheses. And last but not least, what is the correct formula for potassium oxide? Potassium is a +1 ion from group 1. Oxide's a -2. The best choice would be, don't fall for the trick, choice 3. Potassium with a 2, because potassium, even though the word starts with a P, that's not the symbol for potassium, right? And remember, you don't have to memorize it because they give you the list. You can look it up on the back of the reference table in case you get confused, right? So remember, the 8-ite rule means you're polyatomic. If it's ide, you were one of the anions that were created from the periodic table, right? Remember that the pieces and the charges have to cancel each other out to equal 0. Remember that the charges, the number of the ions are written with the subscripts in the formula, right? And remember that if you have more than 1 polyatomic ion, you have to put it in parentheses and put the subscript on the bottom right of the parentheses, right? So there's plenty of practice problems in these review books. I think you guys got this, so we're going to skip that one, and we're going to get to the actual more difficult Regents ones. For example, let's look at this one. When oxygen combines with an alkali metal, now this is from our last session that we had about the periodic table and knowing the names of the groups. Group 1 are called the alkali metals, right? So when oxygen combines with them, what general formula would they have if M represents the group 1 alkali metals? Remember, group 1 means they have one valence electron, so therefore they're going to have a positive 1 charge when they become an ion. And remember, oxides have a negative 2 charge. So puzzle piece-wise, you guys are scared. I see you putting up the answer. A is correct. A is correct. It says if X represents a group 1, and I'm showing you all the variations that come up on the Regents. So if X is the metal now, instead of using M, they use the symbol X. It's from group 1, and they tell you the formula of its oxide. That means it's connected to an oxide ion. Which formula would be correct? Choice 4, which is D. Which properties are characteristic of group 1 metals? And this is referring to our session, our last session, right? Group 1 metals are the ones that lose their electrons the quickest, right? And they're so reactive, we can't find them pure in nature. They're highly unstable, right? But when they lose their electrons, because they're very reactive, they become very stable. And the ionic compounds they form are very stable. So they have high reactivity, and they form very stable compounds. So that's why you find a lot of NaCl, you might find a lot of lithium compounds, right? Because when they do this, they become more stable. Okay. Now we flip the page, and we're going to advance. How do you make ionic compounds for real? Or how do you do it? Well, you take a metal compound, not a compound, a metal element, right? And you're going to react it with a non-metal element. So calcium and oxygen, metal element, non-metal element. So the atoms in here, there's 2 of them in this molecule, are going to take the electrons away from the surface of the metal. That's what's going to happen. Now I have to add some activation energy to make this happen because this guy is holding on to its electrons. So if I give it enough energy, I can force the emission of these electrons onto the oxygen, which are pulling them, and I will make oxide ions and calcium ions, right? But there's a problem here. What's the problem? There's something wrong in this chemical equation. What do you mean? Well, plus 2 cancels out minus 2. That works. But when you play with the chemistry Legos, these particles, the number of atoms on the left have to equal the number of atoms on the right. So on the left of the arrow, I have 1 calcium atom and 2 oxygen atoms. But on the right, I have 1 calcium atom. Wait, that equals that, but there's only 1 oxygen. You can't do that. It's called the law of conservation of mass. The weights over here have to equal the weights over there. But I can't mess with the formula of calcium oxide because that's correct. The only thing I can do is add what we call coefficients. That means increase the number of the particles by putting a number in front of the formula. So, this is very important, what I'm about to show you. Students struggle with this concept. So we'll use the formula that we're working with here, the calcium and the oxygen, if I could do this. I'll raise this over there. So, you have what does this mean? I have 1 calcium atom, I have 1 of these, right? I have 1 of these. These are particles. I have 1 of those, 1 of those, and 1 of those. I'm cooking. I'm trying to bake the cake. This is the cake. But there's a rule in chemistry that the number of particles, which are the atoms within, have to be the same on both sides. So, how could I fix that problem? If I put a 2 here, that means now I have 2 of these. Does that get me closer to solving the problem? Now I have 2 oxygens total on this side, 2 oxygens total on that side, but I only have 1 calcium. But if I come over here and put a 2 in front of here, now it works out that the number of atoms on both sides of this imaginary fence, which means if I'm cooking, I'm going to take 2 of these particles and 1 of those particles, break their bonds, and make new bonds, which are on the right of the arrow. And the number of atoms I started with equal the number of atoms I finish with. Okay? Could you predict randomly, like the scientists did? If I take magnesium atoms and put them next to nitrogen molecules, what can I predict I will get as a product? This is a particle, and this is a covalent. Remember that what we're going to do is we're going to crack the particles and rearrange the atoms. That's how I know did a chemical reaction. I break the old bonds and I make new bonds. What can I predict I'm going to make? Well, we know metals lose electrons. And these are going to be a +2. And nonmetals that are in here, each one of them are going to gain electrons and become, wait a minute, that doesn't work out. Now you could be slick and say, okay, I'm getting good at this, Ms. Langella. I know I'm going to have 3 of these and 2 of those. That's a good prediction. How did I do that so fast? When the numbers are different, you crisscross the numbers. This is telling you how many of those you have. This is how many of those you have, because the common number is 6. So the formula of my compound would be Mg, 3 of them, 3 times a +2 gives me a +6, and 2 nitrides gives me a -6. So I just predicted what I would make. Problem is, shucks, this is not going to equal out because I got 3 Mgs on that side and only 1 on the left. I got 2 N2s on that side. That worked out, right? Because there's 2 N2s on this side. But to fix this is real simple. I use a coefficient. I put a 3 here. That means I'm going to have 3 of these guys reacting with 1 of those guys to make the proper magnesium nitride. See that? Now I'll show you an example of one directly from a Regents, but this could show up. This could show up. The logic behind it is critical in what we do in chemistry. We make products. That's what we do. We play with the Lego particles. So, based on what I said, right, you can predict what you're going to make. Like, this is going to become a positive ion, and the nonmetals in this molecule will become the negative ions. So what do you think you're going to make? Let's see if you're smart enough to figure this out. You want to come up with a prediction of what you're going to get as a product? Just the name of it? What would it be called? This is not easy. This is advanced. This is the toughest question they could ask you on the test in a part 2.
Calcium and +2 ions.
What do you call that guy? Just give me its name. Calcium. And when chlorine becomes a, yeah, very good. You're going to get calcium chloride. Then you say, okay, well, what's the formula going to be for calcium chloride? Calcium's a +2s, chloride's a -1s. What will the formula be?
Calcium with a +1 in chloride.
So it'd be CaCl2, right? So 1 Ca +2 ion with 2 chloride ions. That would be absolutely correct, right? So the key is, can you predict it? And then you have to say, is that balanced? In this case, it would be, right? Because you got a Ca with 2 chloride ions. That gives you 2 chlorines on the right. You got 2 chlorines on the left, 1 calcium on the left, 1 calcium on the right. That works out. That works out. Okay, so the first step is to try to figure out what the formula is going to be. So I helped you out here. Iron and oxygen. I'm telling you, you get iron 2 oxide. Okay? Iron 2 oxide is typically, for example, rusting. Right? That's what that means. You mean an ionic compound that has iron and oxide and iron and oxygen in it. So you would try to write out the formula. Why did they have to tell you got iron 2 oxide? Because you could also get iron 3 oxide. That's possible. So iron 2 oxide, its formula would be, this has a +2, oxygen has a -2. Oh, that works out, right? So the formula is just FeO. But is it balanced? Is it balanced if I just leave it like that? Well, that's problem number one. You got to realize there's something wrong. What's wrong? The oxygens are wrong, right? There's 2 oxygens on the left and only 1 oxygen on the right. So you can't have that. But I could fix it. I could come over here and say, okay, I'm going to make 2 of these particles. But then I have to go back to this side and say, okay, well, I have to start with 2 of those. Right? What about if you took aluminum and oxygen? What would you make? Aluminum oxide. See, you're getting good at it. And these reactions are called synthesis reactions or combination reactions. We're taking a metal and a nonmetal and putting them together to form an ionic compound. But here's the thing, aluminum is a +3, oxide's a -2, so I got a puzzle problem here, right? So how many of these aluminum ions do you think you're going to need? Let's see if you're getting good at this. 2, right? And how many oxides do you think you're going to need? 3, right? Because you're using the crisscross concept, but you had to see the puzzle first. And now the crisscross concept makes sense. So I'm going to get, that's my compound, right? And then what? Well, it's not balanced. See that? It's not balanced. So now you gotta work it like a puzzle. What can I do? Well, a common number is 6 here, right? Will that work? Will 6 work? What do you mean? Well, let's say if I put a 2 here, that gives me 6 oxygens on that side. So I could come over here and just put a 3, because if each molecule has 2 oxygens in it, and I got 3 of them, now I got 6 oxygens on the left, right? And then I could easily fix the aluminums, because 2 aluminum plus 3 ions give me a grand total of 4 aluminums total. So if I come over here and put a 4 there, boom, it's balanced. So you got to understand what we're doing. We're like Betty Crocker cookbook chemistry. We're figuring out how many pieces it takes to make the cake. We're writing the ingredient. That's what we're doing. We're saying you're going to need 4 of these particles to react with 3 of these particles to produce this ionic compound. And that's chemistry. That's chemistry. See, I'm excited about it because this is real. I could go in the lab and recreate this in a laboratory environment. So that's what makes it exciting for me. That's why you see me get all happy about it, because it's real. It's not like a situation where there's too many variables. It's direct. Okay, let me just get my... Okay. So we call those combination reactions or synthesis reactions. And this is directly from a past Regents. Right? Now you're on your own. Now you're on your own. So you prepared for this. You trained for this. So they want you to complete this. So the first thing you got to say is what can be made, right, from taking silver. Now silver, ding ding, silver is a transition metal, but if you look at silver, silver is unique. It only has a +1 charge in its box, right? And whoa, this is ozone. They get a little tricky here. Ozone is an allotropic form of oxygen, which is what we discussed in the last session. Sometimes you can find an element in more than one form, and oxygen is the example of that. But I'll tell you this, it doesn't matter if it's ozone or oxygen. When it becomes an anion, it's going to have the same charge. And it's going to turn into a, what do you call that? When oxygen becomes an anion, what is its name? An oxide, very good. So we know it's going to be an oxide. So we know, again, I go on my portable whiteboard here. Let's see, hopefully we stay beautiful. Okay? So we know that I'm going to get my oxide. So the ozone will become oxide with a -2. The silver, I told you, only has one oxidation state. It's a +1. They don't cancel each other out right now because the puzzle pieces don't equal 0. So what do I need more of? What puzzle piece do I need more of? The silver ion. Very good. I need one more of these guys, right? And that would give me my ionic compound that would have 2 Ags with 1 oxygen, like that. So, our prediction is that the silver will react with the ozone, which is unique, to produce silver oxide, right? I don't need a Roman numeral because it doesn't have more than one option in the box. Next thing is this balanced? No. But I could come over here and say, okay, I got 3 oxygens on this side of the fence, but I only have 1 oxygen atom symbol on that side. I can increase the particle numbers by putting a 3 there. But now I have 3 oxygens on that side, check, 3 oxygens on this side, check. But I got a total of how many silver symbols on that side? 6, right? Because I got 3 of these whole particles here that had inside of it 2 silver ions. So now I need to come over on this side and place a 6. Now the Betty Crocker cookbook will be correct because the quantity of particles on the left side is equal to the quantity of the particles on the right. And I would get full credit. Okay? Now, you should note that up here they didn't ask to balance. Well, they said complete the equation, so that you would have to balance it. Right? That's how that works. Okay. You should note that on the periodic table in the booklet, you find a table I. And table I tells us the synthesis of ionic compounds are highly exothermic. How do you know that? Well, look at this example they give us. If you take aluminum and oxygen and produce aluminum oxide, you have a negative, what they call enthalpy, or heat of reaction. When the number is negative, that means energy is being released. The reason is because what you have here are you have metallic bonds, which we learned in our last session. This is covalent bonds, which are highly unstable. And at the end, I make something with extremely strong bonds called ionic bonds. So therefore, this is very stable. This is loaded with potential energy. This has very low potential energy. So where's the energy go in the chemical reaction? It leaves the reactants and becomes part of the surroundings. So these reactions, you got to step back because energy is coming out. They're exothermic. If you could make them, you could break them. That's a rule in chemistry. So if I can make NaCl by taking sodium and chlorine, if I take NaCl and somehow overcome their strong bonds, I could reverse the process. When you reverse the process of a synthesis reaction, you're just talking about a decomposition reaction. So the opposite of synthesis is referred to as decomposition. So if you know how to make the ionic compound, if you take the ionic compound and give it a lot of energy, or force electrons back into the ions and pull them away from the nonmetals, you could reverse the process. But it's not easy. It's not easy. Because this is very stable, this is less stable. To make them go backwards, it takes a lot of investment of energy. That's why you might have to use electricity to do something like this. Same thing with this ionic compound. Now, but this one here, when you have polyatomic ions involved, they're not that stable. So this is easier to decompose. But you don't have to know what you're going to get when you decompose an ionic compound with polyatomic ions in it. What you need to know is what kind of reaction, what is that called? When you start with one reactant and you end up with multiple products, that's decomposition. That you need to know. So this, I know, will be a decomposition reaction because I start with one ionic compound. Are you smart enough to figure out what's the answer? What will I produce if I decompose this ionic compound? What possibly could I produce? There's no polyatomic ions in it. What are the 2 possible elements I could make? What do you think? Hg stands for mercury. That's right, mercury and oxygen. Very good. Very good. Now these with the polyatomic ions, they're harder to predict, but they're not going to ask you that. But you need to know if I start off with one reactant and I make multiple products, That's decomposition. Now, how do you make a molecule? Those molecules that we were talking about? Well, first you're going to understand covalent bonds, right? A covalent bond is what's inside the molecule particle. So if I had a hydrogen molecule, for example, what's happening is both of these hydrogen atoms need one more electron to stabilize themselves. So what they're going to do, they're going to come towards each other and then reach a certain distance where they can share their valence electrons and overcome the repulsion, because they don't really want to get too close, because their nucleuses are positively charged. They want to repel. So there's certain what they call bond length that has to occur, a certain distance, in order for them to share their valence electrons and overcome the repulsion. This is loaded with potential energy. How do you know that, Mr. Angelo? Because there's a fight going on, repulsion and attraction. So in order for them to stay in those positions, you got to invest energy. So these types of bonds are loaded with potential energy. And they're not stable. They don't want to stay like that. They'd rather form ionic compounds. So the sharing of electrons between the nonmetal atoms will allow them to get that magic 8 that they're looking for and form these unions called molecules. So when you have molecules, you definitely got covalent bonds in them. And we now know polyatomic ions even have covalent bonds in them, right? So this fluorine searches for, let's say, another valence electron. So if you put this fluorine next to another fluorine, then what will happen is they'll come just close enough to share their bonding electron, so that he has 8 and he has 8, and now I formed a unit called the molecule. And this is something that we covered in the last unit, but you need to understand that in order to be able to answer a question like this. There's a problem here. This is an oxygen atom, and this is an oxygen atom. They're not stable right now. So what are they going to do? They want to know, given this equation, which statement describes the changes that are going to occur as the oxygen molecule is produced? Again, this is not stable. This is more stable. So in chemistry, when you go from unstable to more stable, is energy absorbed or released? Released. So in the choices here, energy is released. So I got 3 and 4 as a possible answer. What did I do? Did I break a bond or did I make a bond? I made a bond. When you make bonds, energy is always released. But the bonds are formed. Now I got a molecule of oxygen. And this is why the atoms on the periodic table can't stay that way. They have to do something to stabilize themselves. So they're searching to create bonds to make that happen. And this is how they're going to ask you the question. This is a problem that a lot of students got wrong. So if you're understanding, well, it's a good sign. Okay? And look at another version. Right? Same question, just different atoms. So it's a popular question on the exam. Because I'm pulling these from past exams. Okay? Now, in the cases of hydrogen, for example, you only had a single covalent bond because there's only one sharing of a bonding electron. Sometimes you might have to share more than one. So the formulas of these molecules are based on the number of bonds you have to create. Right? That's how it works. So let's say, for example, hopefully,
contains 1 electron.
Okay, so this is a movie. I'm going to start over again.
Stable duplet configuration.
This is a great movie clip that Learning America gave us. Let me try that again.
Consider 2 hydrogen atoms.
Here we go.
Each hydrogen atom contributes a single electron in the formation of a covalent bond. The 2 shared pair of electrons orbit around the nuclei of both hydrogen atoms. Thus, they form a single covalent bond. A chlorine atom contains 7 electrons in its outermost valence shell.
There goes that bonding electron by himself.
It requires 1 more electron to form the stable octet configuration. Consider 2 chlorine atoms. Each chlorine atom contributes The two shared pair of electrons orbit around the nuclei of both chlorine.
So we put a line there, right? To indicate the sharing.
They form a single covalent bond. An oxygen atom contains 6 electrons in its outermost valence shell. It requires 2 more electrons to form the stable octet configuration. Consider 2 oxygen atoms. Each oxygen atom contributes 2 electrons in the formation of 2 covalent bonds. The 2 pairs of shared electrons orbit around the nuclei of both oxygen atoms. Thus, they form 2 covalent bonds called as double bonds. A nitrogen atom contains 5 electrons in its outermost valence shell. It requires 3 more electrons to form the stable octet configuration. Consider 2 nitrogen atoms. Each nitrogen atom contributes 3 electrons in the formation of 3 covalent bonds. The 3 pairs of shared electrons orbit around the nuclei of both nitrogen atoms. Thus, they form 3 covalent bonds called as triple bond.
Okay, now, we could predict this. Okay, we could predict what's on this movie by being able to draw the little dot symbols for the different scenarios. The first scenario, okay, let's say we go to the scenario with the fluorines. 1, 2, 3, 4, 5, 6, 7. Say, Mr. Angel, why did you do it that way? Well, when 2 atoms face each other, you put the bonding electron between the atoms that are going to bond. So if I had a molecule of fluorine, this fluorine would make its bonding electron face the other fluorines, and then you could draw a line between the bonding electrons and to say that those electrons are now being shared. So now I created a scenario where both fluorines believe that they have 8 valence electrons and it's stabilized. Right? In the scenario of the oxygen, remember that oxygen had 6 electrons with 2 bonding electrons, like so. And this oxygen, again, this is allowable on the Regents. You make the bonding electrons face each other, and then say, okay, if I draw a line here, they're sharing those 2, and now I share those 2, and I have a double bond between the oxygens. And then in the case of the nitrogen, like in the image, nitrogen has a grand total of 5 electrons with 3 bonding electrons. Again, how do I know that, Ms. Angela? Because remember, you could go, there's a lot of ways to do it, like drawing a dot on each side, and the ones that are unpaired are bonding electrons. But you want the bonding electrons to face each other so they can be shared. So this one can share with that one, this can share with that one, this can share with that one. Right? But what they don't tell you is that the more number of bonds that you have between 2 atoms, right, the shorter the distance between the atoms. And that means that could be a problem. Like, for example, if you're in a scenario where you have a single bond between 2 carbons versus a double bond between 2 carbons, which you're learning in organic chemistry probably right about now, the distance between the atoms gets shorter and become more unstable. Right? Nitrogen's only the only example of a molecule with a triple bond that is very stable because the distance is just right. Oxygen's very reactive versus nitrogen. How do we know that? A lot more nitrogen in the air than oxygen. Where does the oxygen go? It goes in the water, reacts with the metals. Nitrogen, and when it's in molecular form, is not that reactive. So it's very inert. So these units right here, that's a molecule. That's a molecule. So molecules are formed by nonmetal atoms bonding either with each other or other nonmetals. That what they also did not mention, that these covalent bonds are called nonpolar covalent bonds because the draw on the valence electrons are equal. Both atoms have identical electronegativity, which is what we discussed in our last session. How would you do it if you had more than one kind of atom? How do you figure it out, Mr. Langella? How do you know how to draw a Lewis dot structure for a molecule? Well, what's always true, let's say water. We know water has oxygen, has hydrogen in it. I mean, it's pretty simple. But I have to tell you that's the #1 molecule on every Regents. So you have to know how to draw a water molecule, and you have to know what it looks like. So all molecules that have more than one atom in it will always have a central atom that sits in the middle of the molecule. And the atom that never sits in the middle, never, is hydrogen and fluorine. They could never be in the middle of a molecule, ever. There's a reason why, which goes beyond the scope of the course, but I'm going to tell you that they never will end up in the middle of a molecule. The atom that usually ends up in the middle will have a low electronegativity. That's reason #1, that hydrogen and fluorine can't, because they have high electronegativities, and it has the most bonding electrons. Those are the ones that sit in the middle. So if you look at oxygen, oxygen has 2 bonding electrons versus hydrogen only has 1, right? So typically what you're doing is you put the atoms together, and if you know that you're dealing with oxygen and hydrogen, hydrogen can share this bonding electron that oxygen has, but it still is going to take another hydrogen to share the other bonding electron. And thus you have the formation of a water molecule. Very important to understand that oxygen is the central atom here. And the fact that one side of the molecule is different than the other, one side of the oxygen has electrons on it and the other ones are bonded to hydrogens. We call molecules like that a polar molecule. It has 2 different sides to it. We'll call those polar molecules. And these bonds right here are not nonpolar covalent bonds because they're between atoms that are different. Once you have a covalent bond between nonmetals that are different, then you got yourself a polar covalent bond. That's what it's called. And sometimes you might have to form more than one bond, right, to satisfy the octet. So if I'm working with oxygens and carbon, for example, carbon has 4 possible bonds it can form. Oxygen can only form 2 based on the Lewis dot structures. So if you try to start put the puzzle pieces together, okay, so one of his bonding electrons can be used to share with another of the other atom's bonding electrons. And then if you put another oxygen on this side of this carbon, they can share the other bonding electron, but you're still short now. So if you had carbon dioxide, that means you only have 1 carbon atom with 2 oxygen atoms. How could they possibly form a molecule? They're going to have to move their bonding electrons in positions so that you can have a double bond on this side and a double bond on that side. So that's hard to visualize. So Mr. John, how do I do it on a piece of paper? Well, it doesn't have to be as pretty as my PowerPoint is showing you. So again, you have to determine who's going to be the atom in the middle. Well, carbon has the most bonding electron and the lower electronegativity. So you put him in the middle of the drawing. And I know I have 2 oxygens because it said carbon dioxide. So there's an oxygen on this side, an oxygen. And in the naming of molecules, we use prefixes, right? And we also make the ending always an "ide." So carbon dioxide means I have 2 oxygen atoms in the molecule. They're not ions, even though it says "ide" in the name, because it's not an ionic compound. So this oxygen has 2 bonding electrons. And remember, when you're drawing the dots, you want to put the bonding electrons facing the atom that they're going to connect to. And you play connect the dots. That's how easy it is on the Regents. This bonding electron can be shared with him. This bonding electron could be shared with that one. Right? This one could be shared with that one, and this one could be shared with that one. And that would be acceptable on the Regents as a drawing for carbon dioxide. Again, this is the advanced questions. Again, I know I did it right when everybody has 8. Right? So the sharing of electrons are saying that they're sharing those 2 pairs. They're sharing those 2 pairs. Cooperate with me here. go. So they both have 8. What about if I drew NH3? Okay? NH3. Well, how many bonds is nitrogen looking to form? Based on the showing, there's 2 paired and 3 unpaired. So how many bonds can nitrogen form? 3. You got it, right? And hydrogen can only form 1. So that's why you got N is going to be in the middle, because I told you the rule, hydrogen's never in the middle. And connected to these bonding electrons, you're going to place hydrogens. Right? And you're going to get it, again, this molecule, NH3. This molecule is classified as a polar molecule because on one side of the central atom there is something different compared to the other side. This side has a pair of electrons and this side has bonded bonds to hydrogen. So one side's different than the other. And what's also important to know, once you have a polar molecule, that means one side of the molecule is more negative. Can you figure out which side of the molecule is more negative? Is it the side with the pair of electrons or the side with bonds to hydrogen? What do you think? The electron side. So that means this side of the molecule is much more negative than this side. This could get pretty complicated, right? Now, I don't like the way that I have this on the PowerPoint. I'm going to show you a trick. It's hard to show the trick in a PowerPoint, but you got to first determine who's in the middle, right? So it's carbon that's in the middle because it has the most bonding electrons, not nitrogen. Carbon has 4. How do you know that, Mr. Joe? Because you draw the Lewis dot structure the right way. You say carbon has 4 valence electrons, 1, 2, 3, 4, right? Nitrogen has 5 valence electrons, so 3 of them. So he could form 4 bonds, he could form 3, and we know hydrogen could only form 1. So again, playing connected dots, he can share that bonding electron. So now hydrogen's happy because it only wanted 2 to be like helium. And then I could take this one, connect it to that one, this one connected to that one, and this one connected to that one, and voila, everybody has 8. Right? He believes he has 8 because he's got 1, 2, 3, 4, 5, 6, 7, 8. He believes he has 8. 1, 2, 3, 4, 5, 6, 7, 8. Everybody got 8. I know I did it right. I know I did it right. So if I go with my PowerPoint presentation, it's hard to show that. It's hard to show that. Okay, let's go to some Regents questions. What is the number of electrons shared between 2 atoms in I2? So you got to draw the Lewis dot structure for iodine first. So iodine has 7 valence electrons. And how do I know that? I go to the periodic table, I look at the Bohr configuration, look at the last digit, it says 7. Draw 7 dots, 1 on each side. How many bonding electrons does iodine have? Does it have 2? Or does it have, you sure?
That's 1.
It has 1 bonding electron, so it could only form 1 bond. So 1 iodine atom and another iodine atom, if they put up their bonding electrons, how many are actually being shared? 2. That's correct. That's what you meant by 2, right? I got you. Right? And then you're going to get simple questions like these here. Which electron dot diagram represents H2? Okay, give me a vote. Choice 3 is correct. Very good. See, the bonding electrons are, sometimes they don't have to draw a line, they just put them next to each other. Right? Which of the electron dot diagram is correct for chlorine? Choice 2 is correct. Right? They didn't draw the line, they put the pairs right next to each other. And this is the most popular question on that Regents. Which diagram represents a water molecule? They purposely don't put all the electrons in the drawing, and choice B is correct. Now you should note, remember that the oxygen side, this is a polar molecule, because if you put the dots in, there's 2 pairs of dots here. So this is a polar molecule because on one side of the oxygen is different than the other. And the side with the electrons is the more negative side of the molecule, and that becomes a major topic in another unit. And just like those reactions we were doing before, You synthesize a molecule by using the elements. Like if I want to make CO2, I could take carbon and oxygen, right? And I could make CO2. Remember that the rule says, is this balanced? Is this balanced?
Yes.
Thumbs up, yes, it's balanced. Well, I got 2 atoms here, 2 atoms there, of oxygen, 1 C there, boom, it's balanced. The life is good, right? But sometimes that doesn't work out. Sometimes that works. Like, if you don't have enough oxygen, you can not get carbon dioxide, you might get deadly carbon monoxide, right? So if your fireplace, it doesn't have a flue that's clear and you don't have enough oxygen, you could produce deadly carbon monoxide. That's why you need to have a carbon monoxide detector at home next to your fireplace, just in case. And this is the chemical reaction. We reduce the deadly carbon monoxide. So this is not a balanced chemical reaction because there's not enough oxygens on the right. But I can't rearrange the particles here because that's based on their bonds, right? So the molecule's formula is based on the bonds. So how do I fix this? What can I do? Add a coefficient. Very good. And this is very difficult. Students struggle with this. The word coefficient. Like, what do you mean? You mean I can't just change the subscript? No, because that's like making a different cake. You can't do that, right? So you can increase the number of particles, right? I can put another CO over here, right? And then come on this side and put a 2 in front of there, and we're all set. We'll be balanced, right? Now we're good. Now we're good. But then when you rewrite this, you're going to put 2C plus O2 molecule produces or yields 2 COs, right? That's how you would do it. So balancing is very important. Balancing very important. Now there are tricks to this, right? There's always a trick to go faster. What you typically would do is you draw that fence, right? Now the technique that I have on this PowerPoint, what I did is I wrote R's and P's and wrote the types of atoms in the middle. This is another way of looking at it, another way of doing it. I like my particle way better, but this is another way. You know that both sides have hydrogens and oxygens, and your job is to make sure that they have the same number of those particles. That's the law of conservation of mass. Right now I have 2 H's on this side and 2 H's on that side, right? And I see I have 2 O's here and I only have 1 O there. That's no good. And I got to use those coefficients to fix that. So if I come on here and I put a 2 over here, that's going to change this number because the 2 is distributed, right? So now that 1 becomes a 2. Now the oxygens are good. The hydrogens are good. It's a balanced chemical equation. It's another way of looking at it. Oh, I'm sorry. That was wrong, right? Because I had a 2 here, so that distributed. That doesn't work, right? That gave me 4 hydrogens, so I had to go back and put a 2 in front of that hydrogen. You didn't catch that mistake. So now I do a recount, and now it's good. Now, the synthesis of a molecule might not always be exothermic. How would you know? You got to go to this table. See, these are all synthesis reactions. How do I know these are all synthesis reactions?
Making one product.
Very good. You end up with only one product. So you take multiple and you create only one. Right? So these are all synthesis reactions. This is an ionic compound versus molecules. I'm making molecules here. And I know some are exothermic and some are endothermic by the numbers of the heats of the reactions. If the numbers are positive, that means I got to invest energy to make these new bonds. That tells you that what I made is less stable than what I started out with. Now, why would that be? Because the type of bonds you're making might not be as strong. So when you make these molecules, the strength of the bonds can be determined by whether it's exothermic or endothermic when you make it. Remember, in chemistry, you break the old bonds and you make the new bonds. The potential energy of the new bonds minus the potential energy of the old bonds will tell you whether it will be exothermic or endothermic. That's how it works. So this is kind of telling you, and it has to do with the type of covalent bonds. Polar covalent bonds are more stable than nonpolar covalent bonds. So if you do a synthesis reaction where you start off with nonpolar and you make very polar, like for example, water has very polar covalent bonds in it. because the difference in the electronegativity between hydrogen and oxygen is large. So the bonds are very strong. So that explains why there's so much water on the planet. You notice that? And these guys here that you make the water with, they have nonpolar covalent, which are a lot weaker and loaded with potential energy. So when I make the new water molecule with these polar covalent bonds, they're a lot stronger than what I started with. That's why that's definitely going to be exothermic. And that's an important chemical reaction because that's what these new fangled electric cars, right? They want to use this chemical reaction because it's clean. You're producing water, right? So they want to be able to use the energy of this reaction to be able to drive a car, for example, instead of using electrical energy. So the fuel cells are based on just a simple reaction of production of water. Pretty neat. That's where we're headed. So here's your example of your really difficult question that will show up on the, I was going to say AP because I teach that class too, but this is a Regents chemistry. But the concepts are the same. What kind of reaction is this? I don't know if they're asking that, but oh yeah, there it is. State why you think this is a, they tell you. See, that's the difference. On an AP exam, they don't tell you what kind of reaction it is. This one, they're telling you what kind of reaction it is, but they want to know why you think, why this is true. Why is it true?
It's making one product.
Right, one product, just like before, right? See, that's why I was telling you that, because I know they're going to ask you that question. It's guaranteed, guaranteed. And then they're going to want you to balance it, right? They're going to want you to balance it, right? Now this has to do with the stoichiometry of chemistry, which is a different unit. But the moral of the story is, that's how you approach this question. And again, if you could make it, you could break it. So for example, if we know we can make water, we can therefore decompose water. So in those new fuel cells, you use hydrogen, oxygen to get the energy to drive the car. And then what's neat about it, the beauty of it is they want to get that water that you produced, break it down to create the fuel that you need to keep running the car. Right? That would be, forget, we would never need gasoline anymore, when the end of oil consumption, if they could finish figuring out how to pull this off. But we know you could synthesize water and you could decompose water, and that's the driving force to them trying to figure it out. Right? So if I break down water, what would I produce? What do you think? You would produce what you used to make it. Hydrogen and oxygen. That's how it works. Again, those with polyatomic ions are more complicated, but they would ask you simple questions like, what kind of reaction is that? And you would have to say decomposition. The names of molecular compounds are a lot easier, but I have to warn you, it's not all about prefixes. But there are two ways to name a molecular compound. One is using the prefix system, right? So the prefix system works where you basically tell somebody how many of one atom you have, and then you use the prefix to say how many of the other nonmetal atom you have, and then the name of the molecule with "ide," right? Again, mono is the tricky one. You don't typically use mono for something other than oxygen. So for example, like this guy using prefixes would be called dinitrogen monoxide, right? And this would be nitrogen dioxide using prefixes. But unfortunately, on the Regents, they not only want you to know how to use the prefix to name a molecule, but they also want you to know how to use the stock system or the Roman numeral system to name a molecule. Okay, so we're going to address that immediately. So N2O is dinitrogen monoxide, right? How would you use the Roman numeral system to name a molecule? Well, what they do, so N2O, dinitrogen monoxide, can be also named using what they call the Roman numeral stock system. It's kind of like when you have a transition metal and you use the Roman numeral. It's very much like that because that's what it's called. So what you do is you look at the last atom. which is oxygen. And you know that oxygen has a negative oxidation state of -2. Right? Just like when it's in an ionic compound. And this is another reason why they give you these other oxidation numbers for the nonmetals, to figure out what Roman numeral you're going to use in the Roman numeral stock system. Oxygen is more electronegative. So that means when it bonds with nitrogen, it will draw the electrons to itself most of the time that it's supposedly sharing. But it's not really sharing. It's like me playing, I'm nitrogen, I'm playing with oxygen with basketballs, and the basketball represents my valence electrons. I dribble the basketball, and then I have to pass it to oxygen, and oxygen gets to dribble for longer than I do. So we're not really sharing the basketball equally. The oxygen gets the basketball most of the time. So the high electronegative atom is always written last in the molecule's formula. That's important to note. And the less electronegative is written first. That's how come metals come before nonmetals when you write an ionic compound, because of the order of electronegativity. So the negative, more negative is always written last in the formula. So oxygen is going to take a -2 oxidation state because it's drawing the electrons most of the time away from the nitrogen in this polar covalent bond. So what charge does the nitrogen have to take in order to cancel out the -2 oxidation state of the oxygen? There's 2 of them. So each one must have what oxidation number?
+2.
Well, total. But each nitrogen atom would have a +1. So in the Roman numeral system, you would write nitrogen, Roman numeral 1, oxide. So that's how you would name dinitrogen monoxide using the Roman stock system. Let's try another one, NO2. Right? Again, the oxygen is going to take its negative oxidation number, but there's 2 of them, which would give you a grand total of a -4. So what oxidation state is the single nitrogen taking? It would have to be a +4. So in the Roman numeral system, you'd write nitrogen, Roman numeral 4, oxide. That's how it works. Okay? Now we're running out of time, so I want to go to a different concept. Once you build a molecule, it's very important to know some key features of the molecule. But before I do that, let's try another Regents problem. They love particle representations because the advanced college classes, like AP Chemistry, uses particle representations all the time. So they're training you for that day that you take that class. So here's a particle, as it says, this filled in sphere represents carbon, and the one that's not filled in represents fluorine. Right? So this represents a carbon, this represents a fluorine. It says which particle diagram correctly represents a molecule of carbon, Roman numeral 4, fluoride. So they want you to draw it, if you think about it. So if you're smart, you say, okay, I'm going to forget the particle diagrams. I'm going to write, if I got a C, how many bonding electrons will the C have? It has 4 valence electrons, so it's going to form 4 bonds. Fluorine has only 1 bonding electron. So it's going to take 4 fluorines to connect to 1 carbon, right? So which diagram would be correct? Which choice? Choice 4 would be correct, right? And then what about this guy? It says, what is the formula for nitrogen, Roman numeral 4, oxide? Well, if nitrogen has a +4, because that's what the Roman numeral is, and you know oxides have a -2s, what would be the correct answer? NO2 is correct. Very good, choice D. Now remember that these covalent bonds that are formed, there are 2 main types. There's the ones that are between identical nonmetal atoms, and the difference in electronegativity is basically 0. Then we call those nonpolar covalent bonds. And there's only one exception. A carbon-hydrogen bond is also classified as being nonpolar because the difference is less than 0.4. But typically, 2 nonmetals are the same, that's a nonpolar covalent bond. The Regents will stay away from that so that they don't want to create any controversy. And if the two nonmetals are different, again, the only exception is CH, then you got yourself a polar covalent bond. That means the sharing, remember the basketball analogy? They're not sharing the basketball equally. One atom that has a greater ability to draw electrons to itself gets the valence electrons most of the time. In fact, the bigger the difference in the electronegativity, the more polar covalent it is, the stronger the bond, right? And anything from 0.5 or less, we consider those to be nonpolar covalent, and those are not stable. They're loaded with potential energy. But as the difference in electronegativity becomes greater, the more ionic-like it becomes. We call that ionic character. When you compare the difference in electronegativity between two atoms and you find the difference is great, like an ionic bond would be, the stronger the bond is. And the less stored potential energy that molecule will have because of that reason. So chlorine has a much higher electronegativity than hydrogen. So along this bond, this guy is going to get the valence electrons most of the time, because he's going to be able to play with the valence electrons. They're going to be around the nucleus of this chlorine most of the time. And the poor hydrogen only had one valence electron. It's hanging out with the chlorine most of the time. So there's an unequal distribution of electrons along the bond, creating a partial positive charge on this side of the bond versus partial negative charge on this side of the bond versus the positive side there, and that actually makes the connection stronger. It's like an addition to the fact that they're both attracted to those valence electrons. There's a partial charge. Once you have charges, that makes them stick together much better than if there is no charges, like in a nonpolar covalent bond. So this bond's a lot stronger because of that reason. You have more ionic character, more like an ionic bond, which makes you stronger and makes the bond stronger, more stable, and less stored potential energy. Because in chemistry, particles don't want stored potential energy. That's bad in the world of chemistry. So you're going to get questions like this. Which bond is most polar? And you would look up the electronegativities. We don't have that. But based on what I told you already, this has got a big difference in electronegativity right here. Right? So you would actually look up the electronegativity of the atoms involved, and the ones with the greatest difference between the two would be the more polar covalent. And then they would ask questions like, which one of these molecules has nonpolar covalent bonds? What would you think that answer would be? Don't be afraid. What do you think? Let's give me a vote. Okay? So then you look at them and say, well, nonpolar only can happen if the two atoms are identical. The two nonmetal atoms are identical. So if you look at the choices, this is the only one that has two nonmetals that are identical to each other. So inside there is a nonpolar covalent bond, but we also know that that's not that stable. That's why chlorine gas is so deadly, right? Because that bond's not strong. It can easily break. Even sunlight can break a chlorine nonpolar covalent bond. They're going to be asked questions like, which molecule contains a polar covalent bond? Remember, that's the one that the atoms have to be different. And choice 3 would be correct, right? And then which electron dot diagram represents a molecule that has a polar covalent bond in it? First, this is not a molecule. He's out. That's an ionic compound. He's an ionic compound. He's out. So now I'm stuck between C and A. And choice C would be correct because the nonmetals are different. Right? Now, I'm just going to go quickly with this topic. There's a certain kind of polar covalent bond that's formed in a unique manner. The molecule, or the polyatomic ion that the Regents always refers to that contains this bond is the ammonium ion. The ammonium ion is basically an ammonia molecule that has an H+ attached to the pair of electrons on the ammonia. So this covalent bond was created in a unique manner where the nitrogen gave both of the valence electrons to share with an H+ ion. So whenever the word coordinated covalent bond shows up on the Regents, it's either ammonia is the choice or hydronium is the choice. And that's because the way the polar covalent bond was formed. So there goes your ammonium ion. So he always has the coordinated covalent bond in it. The other species is this guy right here, the hydronium ion. So those are the only two that have this unique polar covalent bond formed. Notice here, this bond right here, the X's are saying that oxygen owned those electrons that the hydrogen attached itself to. And you should have learned that acids have a lot of these hydronium ions in them. You need to understand when you draw these molecules the correct way. For example, if you drew CH4, this is what it looked like, right? Where these are the bonding electrons being shared with the hydrogens. The molecule will take a certain shape. The certain shapes the Regents wants you to know. You ready? So you get this shape right here. This is the famous tetrahedral shape. I'm sure your teacher made you put the molecules together with toothpicks and styrofoam balls or gummy bears and toothpicks. And you built a molecule that had this shape. It basically looks like a tripod with one hydrogen is on the top of the tripod, and these are the three legs of the tripod. And this bond angle is the most stable bond angle known to man. So this is 109.5 degrees is the angle between these bonds in this molecular shape. You can vary the tetrahedral shape by changing it by this side of the molecule has a pair of electrons. That takes more space than bonds do and creates repulsion, which reduces the bond angles. But they're not going to ask you what shape this molecule has. But they will ask you one that has 4 equivalent bonds. When you have a central atom with 4 equivalent bonds around it, you're going to take a tetrahedral shape. That's one that they guarantee you're going to see if they ask a shape question. What's the other shape question that you might see? Water is a variation of a tetrahedral, and they actually call this the bent shape. That's also a possibility. Again, the bond angles are going to be less than 109.5 because these extra pairs of electrons take more space than bonds and force repulsion, which reduces the bond angles. And then the famous linear shape. If you have a central atom with only 2 areas of electrons found around it, that always takes what you call a linear shape. That's another popular one that has shown up. And the bond angle is 180 degrees in this drawing. I mentioned polar molecules before. If you have a central atom that one side's different than the other, you got yourself a polar molecule. What about if you have a central atom with 4 sides are all the same? Then you have the opposite of a polar molecule. It's called a nonpolar molecule. Which one of these would be an example of a nonpolar molecule? Choice 3, very good. Which one of these would be an example of a polar molecule? They cheat here. They don't put all the dots in, right? So you see that water is the ultimate polar molecule. And then they may do this to you. They just give you the formulas and you got to figure it out. So which one of these you think is a polar molecule contains 2 polar molecules? This you'd have to draw to figure it out, right? Remember, polar, not nonpolar, polar. If you pick choice C, those are examples of 2 nonpolar molecules, right? So you would have to draw it out. Ammonia is another famous polar molecule. And if you drew out HCl, right? The Cl is the central atom. One side has pairs of electrons, one has an H on it. So that's also polar. Why do you need to know about polar molecules? These molecules have forces that make them stick to each other. What do you mean? Well, in chemistry, there's 2 types of attractions. There's what's inside the particle. Those are the bonds. We call those the intramolecular attractions. That's inside the particles. And then you have the attractions between the particles. Okay? So this is inside. This is between the particles. So we're going to focus in what's happening between the particles, not inside the particles. Well, this is very important. We call that intermolecular forces, or IMF for short. And these IMFs are going to control unique things about the matter made up of these particles. The phases they're going to be in, the types of things that they can do, like evaporate, boil. The physical properties of the chemicals will be controlled for the molecular compounds by these IMF forces. For example, these little circular spheres are molecules, let's say, right? When they're in a gaseous phase, there's space between the particles. When they're in a liquid phase, the particles are rolling on each other, right? And when they're set up in a crystalline structure, it's in the solid phase. And water is the ultimate coolest chemical, because water is the only chemical in the solid phase, believe it or not, is less dense than in the liquid phase, right? That's why ice cubes float on top of the water. Icebergs float on top of the ocean, right? And that's unique to water. But the fact is, all particles that are molecules have attractions to each other, and there's different flavors of those attractions. A famous scientist, Van der Waals, studied these attractions. All molecules have this one. They call them dispersion forces. And what controls the dispersion forces of a molecule is how many protons and electrons they have total in the molecule. The more protons and electrons, the stronger the dispersion forces. And you really only see the effect of the stickiness of the molecules when they're really close to each other. But if you take a molecule that's nonpolar and you put it next to a molecule that's very polar, something weird happens. The polar molecule will force the nonpolar molecule to get an instantaneous unequal distribution of charge on it. So for example, oxygen is nonpolar. Water is very polar. But if oxygen comes in contact with water, the oxygen's electrons get basically screwed up. And now you have an unequal distribution of charge on the oxygen, which will allow it to get into the water. Because if you think about it, if the water is so polar and sticking to itself, why would oxygen get in? Now, you're not going to get a lot of oxygen, right? There's a limit to how much oxygen you can get in the water, but some will get in. We call that an instantaneous dipole. When something that's nonpolar gets close to something that's very polar, the polar molecule will induce a polarity on the nonpolar molecule, which will allow them to interact and mix. The more protons and electrons a molecule has, the more a polar molecule can induce a polarity onto it, which will allow them to mix. These dispersion forces that I was referring to, again, has to do with the number of protons and electrons total. So molecules that are really large, with a lot of protons and electrons in them, will have stronger dispersion forces. Okay, here's some examples of even hydrogen molecules. They're going to stick to each other because when they get really close, they sense each other's protons and electrons with opposite charges, which will allow them to stick. But this force is not that strong. And it only becomes important if you squeeze the molecules real close to each other. So they're going to ask you questions like that. Like two bromine molecules, as the distance between the two bromine molecules increases, that means they get further apart, what happens to the intermolecular forces? Do they increase or decrease? They decrease, right? Because it only plays a major role if they get really close, because they're not polar molecules. So, but that explains why certain elements that are nonpolar molecules, why is fluorine a gas versus iodine is a solid? Because iodine has more protons and electrons in them total, therefore its dispersion forces are stronger. So at STP conditions, you're going to find iodine as a solid and fluorine as a gas. That's a common question. So as you go down the halogen group, fluorine's a gas, iodine's a solid, because iodine has stronger dispersion forces because it has more protons and electrons. Bigger molecules, more electrons, stronger dispersion forces. So intermolecular forces of attraction between nonpolar molecules always decrease with, so what's going to make them have less London dispersion forces. Always decrease. Choice 1, decrease in molecular size and increase distance between the molecules will lower that IMF called London dispersion forces. And then look at that. Here's the question I just was going over, right? They're talking about the boiling points. Turns out boiling point is a critical way to measure IMF. The higher the boiling point, the stronger the IMF attractions between molecules. So you notice fluorine has a negative 188 versus iodine has a positive 184. So iodine has stronger IMF. That's important. So boiling point can be used as a measuring tool of IMF. Right? So stronger intermolecular forces occur in larger molecules. So both of these molecules have IMF. And it turns out sometimes the geometry plays a role, right? This has a boiling point of 9.5. This has a boiling point of 38.1. These are organic molecules, which you're probably studying right now. It turns out when they're linear like that, their IMFs are stronger than when they're symmetrical in organic chemistry. So these IMFs are everywhere. Now I have a lot of movie clips that I could show you some interesting experiments of IMF at work, right? Here's a dish of water, right? And I'm going to take a molecule that's polar and place it into the water. Turns out camphor is the stuff that is in Vicks, right? You know Vicks? When you have a stuffy nose and you sniff some camphor, it clears your nostrils. Well, look what happens when you put camphor on water. The molecules look like they're alive. I used to trick my students and make believe these were fleas that I trained. And I brought them in and I placed them in the water and they were dancing. And then I would touch my nose and then touch the water and they would stop dancing. Now that's a complicated phenomenon that I create in class, but there was me touching it and then they stopped dancing. I didn't get that piece where they stopped dancing. But the water molecules are attacking the surface of the camphor. It turns out the water molecules are polar molecules. So once you're a polar molecule, you're going to be attracted to other polar molecules. And that's what's happening. You could actually see the water attacking the camphor as it dissolves in the water. It's pretty neat. And it turns out if you take a water molecule, let me flip this one because we don't have time. If a molecule's polar, we immediately say the molecule has, in addition to the dispersion forces, have another flavor of IMF, which is called dipole-dipole attraction. So once you're a polar molecule, you're going to be more sticky to each other than nonpolar molecules. Because now you on the molecule have one side that's more negative than the other, and that means the other side's positive. So the negative side is going to be attracted to the positive side, and that's going to make them stick, right? But it's not that dramatically different. It's a little bit stronger. It's not until you put a certain feature on the water molecule. So this is what I mean by the polar molecules, right? The negative side on one side is attracted to the positive side on the other molecule, which makes them stick. But the strongest IMF you can create on a molecule, if somewhere on the molecule you place a certain combination of atoms. If you take, let's say, oxygen or nitrogen or fluorine on your molecule and connect it to a hydrogen, because of the big difference in electronegativity and because the atoms are really small, right at that spot, you're going to have a really, really polar spot that's going to allow the molecules to stick to another molecule with a force so strong that we almost equivalent to a bond. We call this kind of stickiness hydrogen bonding. That's the name of this intermolecular attraction. So the hydrogen of this molecule is going to be attracted to the pairs of electrons on this oxygen with a force that's so strong, it's almost equivalent to a bond. But it's not really a bond, it's an intermolecular attraction. So water is sticky to itself, right? Water beads. You know, think about it. You have a screen on your window and it's raining and the water doesn't come through because once it hits the metal, it sticks to the metal, then it sticks to itself and it drips off the screen, right? That's because it has this feature. Once you have this feature on the molecule, that's going to be a really sticky spot. This hydrogen is going to be really positive, this oxygen is going to be really negative, and now they're going to stick to another molecule that has the same feature. So water molecules love to stick to each other, right? And they create interesting particle arrangements. Like in the solid phase, they create these crystal structures that have holes. A water molecule in the solid phase has holes in it, which is that's why it floats on water, liquid water. Hydrogen fluoride is very sticky because you have that hydrogen connected to a fluorine. Once you have that feature, you have a very unequal distribution of electrons on the molecule. The fluorine side's really negative, red means negative, and blue means positive. So the positive side of this molecule is going to want to stick to the very negative side of the other. But you only have that if you have that unique connection on the molecule. Here, you're learning organic chemistry, right? So alcohols have that feature, right? So they're very sticky right at that spot. So does this alcohol, has 2 of them, those features. This one has 3. So it should be this chemical glycerol, 1, 2, 3, propatriol, that organic chemistry nomenclature, right? Has 3 OHs. The more OHs you have, the more sticky you become, right? And that stickiness plays a major role. It plays a major role. We don't have time. Here's a pretty interesting demonstration. I placed alcohol in this little container. I got to show you this. This is so cool. So I placed some alcohol in here, and then I decided to take an iodine oil mixture, because they're both nonpolar. So when you're nonpolar, nothing's stopping you from mixing. And this container had alcohol in it. So when I dropped the little droplets, right, you can see them. They look like little beads, right? They formed the beads because they don't dissolve well in the alcohol, right? Because these are nonpolar. There's a rule. Chemicals with charges mix well with chemicals with charges. Chemicals without charges don't mix well with chemicals with charges. I think you teach them how to use like dissolves like, but that's not necessarily true because oxygen dissolves in water, right? So it really has to do with charges. But check it out. See all those little beads? Now I'm going to add water to this, and watch what happens to the beads. Look what's happening. I had all those beads, and now I have less beads as I add the water to it. Well, why is that? Well, the alcohol and the water are both polar, right? And they both have hydrogen bonds, so they're sticking to each other. And in turn, the oil and the water don't mix well. And the water and the alcohol love to bind to each other, so the density of the solution changes, makes the oil droplets rise. Looks like a magic trick, right? And the oil droplets are forced to come together because the water and the alcohol are pushing them away. They want nothing to do with the oil and the iodine because the oil and the iodine are nonpolar and the alcohol and the water are polar. So the alcohol and the water want to stay together and force the nonpolar chemicals away. That's important to note. These IMF forces control a lot of properties of the liquids, but unfortunately we ran out of time. But these are important properties that are being defined by the intermolecular forces. So you guys did a good job. And thank you for coming.
Expert teachers and educators at Learn America have created an online platform that helps students better prepare and improve performance in standardized tests in math and science. Step 1. Our unique methodology involves taking pre-assessment tests. Students take pre-assessment tests to determine their skills, knowledge, and readiness required for taking a course. Students are provided a detailed progress report at the end of the assessment to determine their strengths and weaknesses, and areas to focus on in order to achieve higher success in the course. Students access the courseware through the Learning Management System, or LMS, that is available anytime, anywhere, either through a browser or through the apps for the Android or iOS platforms. Students will have direct access to instructors, view any posted course announcements, and view a calendar of upcoming course events such as homework due dates, assessments, and so on. They may also download a learning report detailing any of their course activity, such as assessment scores, anytime. Step 2. personalized learning plan developed based on the student's test scores in the pre-assessment test. The LMS includes an ebook for each course that provides theoretical concepts broken down by chapters and topics. Each chapter includes diagrams, graphs, or animated videos to provide visual demonstrations of the theory. The LMS platform has several features to make the learning process easy. Students can highlight important information, take notes, use the online calculator, and unit converter. Our expert teaching staff has created an extensive question bank that provides self-assessment questions in the form of quizzes after every chapter. These tests provide students a quick assessment of what they have learned in each topic or chapter. Students get to view the results immediately and provide an instant view of what specifically needs to be revisited prior to moving to the next topic. Step 3. Adaptive assessments and formative updates, where students then experience a series of assessments. Formative assessments are configured to reinforce the essential concepts behind major topic areas and to prepare students for more rigorous assessments as they march towards exam readiness. The assessment results allow students a full 360-degree view of the courseware to reinforce the learning, and step-by-step detailed solutions to reinforce problem-solving abilities. Faculty will use the formative assessment results to further guide the students. The students are then put through a more challenging adaptive assessment process. Much like progressing through a video game's levels, students climb the competency ladder by mastering one concept at a time. The adaptive assessments culminate in a mock final exam covering the complete course. Step 4. Interactive moderated online forum. Students get an opportunity to participate in online discussions. Here, they can post questions and share information with other students taking the course, as well as faculty and teaching assistants. Step 5. Progress report and intense interactive review dialogues. We provide a detailed, personalized progress report to view course progress. Students may participate in faculty-led review dialogues. This is conducted either in person or over an online conference. Step 6. Ready review. Towards the end of the course, as their test approaches, students take a final summative assessment that details specifically what sort of outcome they can expect from their exam. With this assessment, students can dig deeper into what they need to know. Practice exams are available anytime and can be taken any number of times.